Oh, they're great. They're kicking up a storm.
One of them's here.
Kicking up your leg too if you get between them and the goats.
All right, let's get started here, guys. What we're doing today, we're going to do a video for our FANUC certification. This video will be sent to FANUC. They will look at it. They need a video of a presentation in the classroom, and that's what this is about. I will ask you please turn off your cell phones, no interruptions while we do this. Please don't ask any questions during the presentation. There's a good chance that I will answer any of the questions you might have during the conversation, and then after we get done, what we're going to do is go into our computer lab, and we'll run RoboGuide, our software, to simulate the robot. I've got some exercises we're going to do, and then from there, we will come, I'll set the robot up in the lab, and we'll actually manually run the robot. In order to get started,
I think I got my phone on. I don't know. I never turn it off.
our subject for today is frames. So before we get started, I'd like everybody to point to their left. Please put your hand up, point to your left. Now why, some of you guys pointed over that. Why are we pointing in different directions? The reason we're pointing in different directions is our point of reference, or our frame of reference, is different from everybody. Each of us is oriented different. My frame of reference, I'm thinking this is forward. For you guys sitting there, forward is towards the board. For somebody's got their head down, and you know, it's all different. The one that we think of as being universal, but it really isn't, is up and down. If we point up, we would be pointing towards the sun. People in Australia point up, no, they're pointing at the stars. So even up and down is different depending on your point of reference. Now this robot also has a point of reference, or its view of the world. And its view of the world is based upon how the robot is mounted. This robot is mounted on a horizontal flat surface, typically a pedestal is where the robot would be mounted. And its orientation is, we think of this as the rear of the robot. So the robot is actually in this position with the cables coming out the rear of it. We're based on the Cartesian coordinate system. Cartesian coordinate system, as you guys remember from algebra, is X, Y, and Z. That's our basic coordinates. So the robot, the X coordinate for the robot is this direction. So when the robot moves, if we tell it to go in the X direction, it will move away from the cables here. The Y representation will be at a 90 degrees to it, and then the Z, in this case, is up. Now that's not always the case.
Now I have a question on that Y movement. Is there a positive and negative, or?
I'll get to that in a moment.
Okay.
So here we said X is opposite the entry point. So the positive X on this robot would be this way on the one. The Y is to the robot's left. For this robot, positive Y is this direction.
Negative is left.
Positive Z would be straight up. Problem is, that doesn't always work. It is possible to take a robot like this and hang it on a vertical column. It's possible to hang it from an overhead beam, or actually from a gantry crane. There are robots that actually traverse across the factory floor to reach, pick up a part, move across the floor. From this robot's perspective, when it's hanging upside down, this is positive Z. We think of Z as being up. This robot thinks of it as being in that direction. This robot thinks the positive Z is coming out of the board. Totally different orientation. The robot doesn't know. Each has their own frame of reference. That's why we call it frames. We have a rule called the right-hand rule to determine which frame is which. In order to do this, I get each of you to stick out your right hand and point straight away from you. That is the plus X. This robot right here, if I'm standing in this orientation, plus X is in that direction. Doesn't mean if you turn a cabinet, you flip it upside down, plus X is still that direction. If you extend your middle finger at a 90-degree angle, 90 degrees, Bill.
My whole finger's been broken many times.
That is the positive Y direction. In this case, I said it would move to the left, which it does. And then Z is with the thumb up. That is your positive Z. With your right hand, it's oriented just like this. X, Y, and then Z. As you can see here, depending upon the orientation, it could be upside down, could be twisted, rotated. The robot doesn't care. It all depends on how the robot was mounted. We have 3 additional axes. This machine can move in 6 degrees. It can rotate here at the waist. It can rotate at the shoulder, at the forearm, which we think of the forearm, or kind of at the tool mounting point, which is the ball. Based on our X, Y, and Z, we have 3 different axes or motions we can think of. The first is roll. Roll, we can think of something as rolling from left to right. I think of it on a boat or an airplane. Roll from left to right. That's rotation about the x-axis. The next is pitch. Pitch we can think of as rolling up and down. That would be rotation around the y-axis. Yaw rotates this way. It's like if you were skidding sideways or something. That's just like in a boat. Yes, sir. It gets a little confusing when you think about which way is positive X, positive Y, positive Z, in the yaw, pitch, and roll. The way to do this, we'll do the Z first, or yaw. That's the easiest. You're pointing up, you take your fingers and wrap like that. That would be the positive direction. And you can see that's how it's indicated here. That's our positive. For the other, if I want to do the Y, for instance, for my roll, I put my thumb that way. My roll Y is positive in that direction. And for X, I would turn my hand this way. My thumb would be going in a positive X, and this would be our roll, or this roll on the X, and then roll is the other one. Easy enough to remember. The hard part is sometimes doing the gymnastics to get your hand in the proper position.
Oh, I can't do gymnastics.
Now, the problem we have with this, well, a couple things happen. First of all, the robot's orientation, its point is 0, 0, 0, is located in the center rotation about the waist at the height of the shoulder. This joint right here, joint 2. If I ask this robot to move to the point 0, 0, 0 from its perspective, it would actually be inside the robot, inside that joint. So the robot can't go there. And what it would be moving at that point is the end of the arm. At the very end of the arm, where that plate is mounted, where our tool is mounted in this case, we would be asking that to go to Z position. It certainly couldn't do it. In order to do that, we have to, well, now the robot knows at this point where the end of the arm is. It's got all the geometry, it's got sensors. Typically when we do work with a robot, we have a tool of some sort mounted on the end of the robot. The robot arm itself is not doing the work. We have a variety of tools we can use. If, for instance, we used I'll use a screwdriver as an illustration. If I mount the screw on there, I don't care where the end of the robot is, I care where the point of this screwdriver is. I need some way to tell the robot where the point of that screwdriver is in relationship to the end of the arm. And that way, if I tell it move the point of my screwdriver to such and such a point, coordinates, it will know where to go to get it there.
Do you have to allow for that screwdriver as far as, if you put that, if you have a screwdriver in that robot, do you have to allow for the length of the screwdriver?
Yes, that's what we're going to look at.
Okay.
Next frame. Now, in here, within FANUC and within the RoboGuide software, and on this presentation, they use a green ball. So like I said, the robot believes the end of this ball is the location it knows. That's fixed through the geometry of the arm. It knows where that is. If I'm holding a screwdriver, now I need to know where this point is. In order to establish that point, there's a few different things we can do. Well, let's look at this first. Here's a couple of different tools we could have. This is a tool that could pick up, for instance, a paint can. Reach down and pick up a paint can. Here's another tool. This is another gripper. You'll see in this case, this tool has it set so that the reference point is at the very end, in the center of where it would grip. So if it goes to pick something up, it would pick it up at that point. This, the point, I have it set up here, meaning when it went to its 0 point, it would actually be around the outside of that can. It really doesn't matter, as long as the program, you know where it's at. And then we tell the robot the correct place. We can tell it to go get that can, and it will know at what height, what location it needs to be. Now that's the simplest case, is a tool like that. It is also possible to have a tool like this that is not just straight out. Actually, in this tool, we have to tell it how far this wrench is offset in this axis. In this axis, it could be twisted this way, so we have some rotation. This wrench, now the screwdriver, if I put the screwdriver on a screw, I can just turn it here. If I just turn it, I get this motion. Obviously, that won't work. This robot needs to know where the center of that is, because that's where the work is happening. To do this, we'll use our tool frames. I could actually have multiple tool frames, up to 10, set up in a robot. I could tell it use this end of the wrench, and it would do this motion. If I told it use this end of the wrench, it would use the other motion. In order to do that, it's not just twisting the wrist. It's got to move probably the waist, the shoulder, the elbow, a lot of complex motion, and they have to move all 6 axes in order to accomplish that. The question is, how do we set that up? There are multiple ways. One way we can do it, and it's actually the next slide, is direct entry. If we know the geometry of the tool, if I know exactly how long this screwdriver is, if I know that it's 25 centimeters from here to here, I can go into the screen, on our key spin, we go to menu, setup, frames, frame, select the frame I want to set. I can put in values directly for X, Y, and Z if I know what my offset is here. This would be pretty simple. And we'll do that in the lab. I'll show y'all how to do that.
Now, what's the W stand for?
Yaw.
Is it okay they didn't put a Y in there?
We can't use Y. We already used a Y.
Oh, okay, okay.
So that's why we use yaw.
I know the pitch and roll, but I mean the P&R.
Another method we can set it up if we don't know the exact geometry is what we call the 3-point method. In the 3-point method, we will take a part. I'll use this as an example. I have the tool. I can drive my robot so it just barely touches this and then set it. And I would set it by going into menu, setup, frames, go through the series of menus. I can tell it where that point is right there. Now it knows where the arm is, it knows the rotation, knows everything else. I bring this to another angle, I do it a second time. I bring it and do it again a third time. If each of those angles are approximately 90 degrees to each other, we will determine 3 planes. Those 3 planes intersect at one point, and that robot will know exactly where the end of the screwdriver is. And it does all that complex spherical math for you. Very, very cool stuff. The problem with it we have is, if I wanted to put this screwdriver in that hole right here, I could drive it over this way, it would know where the end of the hole is, but it doesn't know this way. It would have the location, but not the orientation. In order to go in this hole, I have to have it straight up and down, all the angles correct, and the location.
So that's your pitch.
Yes. To do that, we use a different method called the 6-point method. The 6-point method, same idea. We point to it 3 different ways and we rotate it, and it does even more complex math. And it will know, if I want to put the screwdriver in that hole, it will know where to go and all the angles it needs to be at in order to go straight in that hole. That's the direct entry. Other methods, I said the 3-point method, we'll know the position, but not the orientation. We also have to know the orientation in order to do a lot of this work. The 6-point method is beyond the scope of this particular discussion, but once again, we can do that in the lab. We won't have time today.
Do you manually do this?
We'll look at it.
Do you manually do this?
It's all done manually.
Okay.
We will first do it on our software. We have a robotic software. We move our robot around. We touch it off, and it will do it that way. Then we will physically do it on the machine.
Okay.
Touch it off manually one thing at a time. User frames. Now the problem we have, if I have a block, I know where the end of the tool is, but I don't know where my work is. My work will vary depending upon the part that I'm trying to use. Now this robot, we're going to assume this tool was touched off. It knows the geometry of the tool, but I have a block here and it's supposed to put this in the block. Problem is that block is jacked up on an angle, twisted and rotated. So if we were trying to manually to put this in that block, trying to jog that robot to do that is a serious pain. We don't want to do the geometry to do it. The robot can do it for us. In order to do that, we're going to set up a frame, a user frame for this particular part. In order to do that, I'm going to back up. In order to do that, I will take my robot and I will touch it at my origin of the part, the corner of the part. That would be my 0, 0, 0 location of the part. I will move my robot in a positive X direction. It doesn't matter whatever we say on that block, it does positive X. It does not matter what the orientation is, the robot will make the correction. Touch my tool right here, and each time I'm in the menus and select that point. Then I go to the positive Y, which would be over there. Once I set that robot will do the calculations. It will know the orientation of that plane. So if I tell it move the tip of this tool to that plane, or to that point right there, it will automatically orient and it will go exactly to point 0, 0. Now you can imagine if we didn't do this, and I told the robot, let's assume these holes are 20 millimeters apart. I tell it to move 20 millimeters in the Y axis, or the X axis, it may come straight over here, and actually because the way its block is jacked up, it would actually hit the block right there because it has to move in the Z axis and the X, the Y. It's got to do all the fancy trig in order to get directly over the next hole.
Does it understand the pi? I mean, you know, like if you tell it to move 20, is it going to understand that you want it to go 20 to the center?
I want it to go 20 along, if I said this is my X-axis,
yeah,
at an angle twisted 20 in that direction.
Okay.
And if I looked at my blueprint for this part, these holes may be 20 millimeters center to center at an angle. But when it's this way, because the trig, I can't move 20 centimeters.
Okay.
One thing I was talking
Okay,
about.
that's what I was,
It does all that for us. We tell it move 20 centimeters and it will know where to go.
cool.
At this point, it knows where the end of the tool is. It knows where our part is located. Now this can be a fixture or a part. I can tell this robot at this point, put this in the first hole, take it out, move over 20 centimeters to the next one, move over 20 centimeters, and it will find each hole in sequence, and we can program it to do that
Okay.
very easily. I don't have to do any trig.
Wow.
At this point, what's cool about it, because it's doing all this math, I can have multiple fixtures. I could have the robot take this pen, and I set up the same frame, the user frame we call this, or for our fixture. I have one set up here and one here. I tell it, use this frame and stick that in the first hole, and it'll go stick it in the hole. It'll know where that hole's at. I can tell it, hey, go put this in this hole, totally different orientation, and if I tell it I'm using this fixture, it will know where to go, and it would put it in that hole.
And it knows the difference between fixtures.
We have to tell it which fixture we're using.
Okay.
If I pick up a different tool, I could have an offset set for that. I tell it I'm using tool number 6 now, and it will know the relationship automatically between tool number 6 and each of these fixtures. It does it for us.
Wow.
Makes the programming so much simpler.
Wow.
Wow is right. It is very cool stuff.
It is. That's sweet.
Some of you guys know a little bit of basic math. Imagine the spherical geometry and calculus is required to figure all this out. The machine does it for us. So, anyway, we're going to wrap it up here. That's all the presentation. We're going to go into our computer lab. We're going to run the Robo Guide, do some of these exercises on the software, and then we'll go to the lab and actually do it on the machine. So, thank you, Melissa.
Yeah, cool. Good deal.